So this is the Algebra 2 Semester A Unit 1 Functions tutorial. So let's actually go ahead and jump into slide 5, which is the starting of the warm-up, and we'll go ahead and continue on there. So, so have you ever been on or seen a ride like this at the fair or amusement park? So it's pretty much one of those rides where you sit, go straight up, and you fall down. So they're going to give us some key information about this ride specifically. So it says, imagine you're being strapped into your seat at the bottom of this 350-foot tower with your feet dangling just above the ground. You make the trip up the tower at a steady rate of 20 feet per second. Stop at the top of the tower to hang for a few seconds, and then suddenly drop a free fall of 288 feet. The trip of up the tower, excuse me, is a linear relationship. The height of the rider's h is equal to the constant rate multiplied by time t since they began the trip up. The free fall down the tower is a quadratic relationship with the distance from the top to the bottom of the free fall, d, is modeled by the equation where t is the time since the free fall began, and d naught is the initial height distance above the bottom of the free fall. So when we take a look at this, and kind of accidentally gave a little bit away already for the first one, just for the trip up here and this uh-oh, what happened? I accidentally clicked on that and trying to exit out of this. Sorry about that. Okay. So for the trip up, we are going to multiply the constant rate times the t, or by the time t. We don't know exactly what time, so we're going to represent that as t. Now, what is the constant rate of the ride actually going up? They already told us that it goes at a steady rate, or in other words, at a constant rate of 20 feet per second. So right there, we have our 20t, right? So if you want to know how far you've gone up in 5 seconds, you plug in 20 times 5, 100 feet, because again, you're going 20 feet per second. So that is going to be our h right here. To find the height that you're at, it's going to be 20t. So that's our linear relationship. Then we have the free fall d. So d is equal to, they already gave us a portion of the answer there. It's negative 16t squared plus d naught. The question is, what is the value of d naught? So right there, you will type in negative 16. We should have our t, and let's go ahead and press on this button here to put the squared, plus what is d naught? So if we look at d naught, they did say d naught is the initial distance above the bottom of the free fall. So pretty much how many feet does the ride actually fall? We know that the ride is 350 feet. So if we think of this as like a visual, this is at 350 feet. And now if you've ever been on one of those rides, you don't start completely at zero, but because it's already elevated at a certain point, but it goes up and then it kind of stops here because you technically have some board, kind of like the name of the ride. So you don't go all the way up, but we do know how many feet you drop. It's mentioned right there, 288. So then we have our plus 288 feet of how much you actually drop there. So go ahead and make sure you submit that there for the warm-up. And let's go ahead and continue. So we are talking about two different functions here. The linear is just a line, it's just a line, but it's any line that can be represented as a linear function. And then a quadratic function is a parabolic shape. So if you think about it, we know that this is everything is represented based off of time. You can say that this is your h for the height or even the distance. So at 0 seconds, you're at the bottom of the ride. Then you have to go all the way up. You reach to the very top, the top of the ride, and then you free fall and you drop. So that's why it represents our quadratic relationship, because this is a function of time. And again, the height, right? Depending on what time or how many seconds you're into the ride, it will actually tell you the height. So what does that also mean? Both equations are relationships because they are a show of how two quantities are related. In fact, they're both special. They're types of relations called functions. So functions, you're going to see functions represented in three different formats. You'll see it in a table, um, in a graph, a table, sometimes a verbal description, or if you're not given like a table, you're given ordered pairs. So it's a relationship between two variables in which each value of the independent x maps onto one and only one value of the dependent variable y. So to kind of summarize that, your x cannot repeat. That's like the simplified version of it. Is your x is that independent variable maps to one. So if I think about it in terms of a graph, right? If I bring back the graph that I had before, if this is considered a function because say at 3 seconds they're at like almost towards the top point. 3 seconds is the only time there. There's not going to be another seconds where it or I was about to say incorrectly. 3 seconds only corresponds to one height. Now I can have a height repeat because at this point right here, you're going to be at the same height, but that's at a different time in seconds. Again, your independent variables or your x cannot repeat. And that's kind of to like almost summarize the idea of what you're going to be seeing in terms of functions. So let's take a look at that one right here after slide 7. Function representations, kind of like a little bit what I've already mentioned before. It might be given to you only in 3 different ways. You might see it as a graph, a table, or ordered pairs, sometimes a verbal description. So function representation. You have your independent variable and your dependent variable. Your independent variable is anything that corresponds to the x-axis or the x. Your dependent variable is your y, or consider, they have different names for it. Dependent output, a y value. Independent variable is input and also your x value. So kind of like a little bit of it's just reiterating, right? Your dependent variable depends on your independent variable. So we have 2 different quantities here, time and height. If I tell you the height I'm at, it kind of defeats the purpose because your time could be different, if that makes sense. Now I'm like thinking to myself, probably doesn't make sense. You don't know where your height will be unless you have your time. That's what pretty much it is. Your input variable will always have or your dependent will always depend on that independent variable. So time is perfect, right? Time in the sense that, okay, 3 seconds. What does this correspond to? Oh, it belongs to this height. And again, but if I say what belongs to this height, it kind of defeats the purpose because we don't know the time in itself. We probably can go work that way and backwards. It's just that concept of independent variables are pretty much our input and it should not repeat. Those are the ones to be declared as a function. So how do we function notation is another important thing. You're going to start seeing before you used to see, let me give it an example right here. Y equals, let's say 2x plus 3. Now, y equals 2x plus 3, I can tell you it is a function, but to clarify it is a function, I can say f of x, that's what we're going to call it, equals 2x plus 3. Now, y and f of x, They are very similar there. If anything, they're the same. But the only reason I write it as f of x is letting me know that it is a function. And my variable inside that parentheses is x. And that's what you're going to see within the equation. So if it say this was a t, and here it would be also a t. F is just the name of the function we call it. So you already saw in the warm-up, we saw h of t, which is a function of time or based off of time, which gives us the height or h. So you'll see different setups like that. So let's take a look at this one here on slide 9. They're giving us back the formula that we saw in the warm-up where it's d of t. So d of t, the function name is what I call say d. T is the variable that we need in order to plug it in. So here they're telling us that t is going to represent that time. So it says, suppose we want to find the distance of the riders at the are from the bottom of the free fall after free falling for 2 seconds. So it says using the quadratic equation, we substitute 2 for t. So if you kind of also look at it, it lines up d of t, d of 2. You're trying to find out what's the height in 2 seconds. Negative 16t squared, now it's negative 16 squared, plus that 288. You go ahead and continue solving. You get d of 2 is 224. So what happens if I want to go reverse? So I know I kind of, it didn't make that much sense when I was describing the input and output, because what happens if I give you the height and you find me what time you are at that specific height? And that's what they're actually doing here for you. So it says, so the distance, that was already from the last one. I'm reading that last paragraph there. How about if we know how long it takes for the riders to reach a height of 250 feet on their way up to the tower? This time, we're giving you the output. So it's very important when you're plugging in these values that you identify which value it and what type of value is it. Is it your variable, or will it be considered the function of it? Like, what is it equal to? That's going to make a big difference here. So here they want us to plug in 250 for h of t. So 250, it doesn't, they're not going to say 250 seconds. They did say it's 250 feet. So by using that first linear equation there, they've replaced h of t for 250, and they set it equal to 20t, which is already set. And then what we're going to go ahead and do is we're going to solve for t. So from there, we're going to go ahead and isolate the t value by dividing 20 on both sides, which they did for that for us right there. So 12.5 is equal to t. That means 12.5 seconds into the ride, they're at 250 feet. Moving on to slide 10, let's go ahead and answer this question here. And again, dealing with functions. Okay, so with this one right here, we have two functions, right? F of x equals negative 9x plus 14, and g of x equals negative 3x squared. So down below, the first sentence states, if x equals 6, then f of 6 is, or equal to. So what we're going to do is that we already know what f of x is. We're replacing the value of with x with the value of 6. So once I write out f of 6, I'm looking at function f, and instead of before that used to be the variable x, and we're gonna, every single time we see the variable, we're gonna replace it with the value of 6. So in the beginning we have negative 9, and instead of, and I have my x there, I'm gonna place parentheses and I'm gonna place my 6 there. And then we're gonna go ahead and do plus 14 to continue. You'll go ahead and multiply, add that 14, and you'll enter your value there. And the next one, it says g of x equals negative 48, then x is equal and x is equal. So here it is a head indicator. You're gonna get two answers. So this one is set up differently. It's not where you plug in the value, they're telling you g of x. So I'm gonna replace this whole thing with that negative 48. So instead of g of x, I'll be writing out negative 48 is equal to, and then I'll continue on writing negative 3x squared. So this one, if you did the previous tutorial, in what is it? I think it's inequalities, something with inequalities. You're gonna go quadratics and inequalities. There you go. You're gonna go ahead and solve. Here you'll be dividing by -3 on both sides. And don't forget that final step to get, because again, you want x, not x squared, you're going to have to take the square root. When you take the square root, don't forget that there's not only a positive value out of it, a negative value too. So when you enter into the calculator as well, it's only going to be the positive value. Remember, at the final step, it is a plus or minus whatever number you end up getting. So go ahead and continue solving that on for side 10. Moving on to side 11. So again, so far we've seen a little bit of how functions are represented, both verbally and as the equations. We can also represent the function relationship in graphs and tables. So on the right hand side right here, we're still using that same example from the warm up where it's h of t equals 20t. Remember, that is giving you the height as you're going up the ride. And another thing too is, remember when I said that pretty much your independent variable cannot repeat. So you can't have like 2 comma 3 and then 2 comma 10. It's not gonna, that's considered not a function because your independent variable is repeating. So when you're looking at a table specifically and they ask you what are your values for like is your function, by looking at the table, is your function or by looking at the table, is it a function? There you go. You're gonna technically look at your input data, which is the x or your independent variables. In this case, it's a function of time. Also, take a look. They all not only give you the table, they also graphed it for you. On the x-axis, you have time. Time represents for t. You have 0, 5, 10, 15, 17.5. None of those values repeated itself. It looks good for a function. Same thing for the quadratic. Now the quadratic, I think I did talk about it a little bit earlier that I mapped it out to look like an actual parabola. So here, their starting point is not at 0, and I think that's what I did, and that was by mistake. The idea for this one is that you're starting at, once you're at that very top of the ride, then we're going to talk about all the time when you're dropping down. So that's the explanation here. Also, if you take a look, all these are two separate functions. One is about going up the ride, the other one is dropping down. So they're like two separate in itself and within one word problem. So again, right there we have 0, 1, 2, 3, and 4. None of those values are repeating itself, so this is considered a function as well. Another way to test out a function, especially when we have graphs, is you draw a vertical line. So it's called the vertical line test, especially if you have a graph. You can draw the vertical line at any point. It passes if it touches the function or the whatever you have graph only once. So if you look, I drew my vertical line here. It touches that line once. You can draw it anywhere and you can draw multiples, as long as again it touches one and one, it's considered a function. If I do it here, there, this is all considered, it passes. Let me give you an example when it fails. When you have a graph that looks like this, let's just say like this, a parabola that opens up to the right hand side, and I draw my vertical line and go right here. Not only does it intercept here, but it also intercepts here. So this actually fails a test. This is considered not a function. So that's what you want to keep in mind. Let's go ahead and move on to slide 12. So function representation. So when it says age group to writers, you're going to go ahead and see that that's considered a verbal description for them. So also, if you think about it, it's say for this one specifically, in the 10 to 19 age group, there are 48 writers. The 20 to 29 age group, there is half the amount of that amount. So instead of 48 writers, take half of that. That's how they get that 24. And then in the 30 to 39 age group, there is half of that. So it's decreasing by half. For each age group, it's not repeating. So they're separated in its own age. So one group, you don't have one person that fits in the first group in, or you don't have a person that has an age that not only follows under the category of the first group, but also in the second group. They're in this. This is considered an actual, or it considered a function, and not only that, an exponential function because it's decreasing by half. In terms of the riders, again, age group would be your independent variable. Riders would be your independent. Let's take a look at the equation one. So the equation here for this example is actually based off of the verbal description. A is your age group, and n of a, when you plug in that a value, depending on the age, you're going to actually get the amount of riders. So we start out with originally 48 riders, and we take half of that for every group increase we have there. So it says to find the number of riders in a specific age group, substitute your appropriate values of A into the equation and simplify. So for example, the 50 to 59 age group is represented by A is 4. So if you think about it, the way they separated those groups of ages, they counted like this is 0, this is 1, 2, 50 to 59 would be would be the fourth group in that or age group category. So they plug in the value of 4. So instead of n of a, it's going to be n of 4. 48 to the half power, or half to the fourth power. Sorry. So that variable a got replaced with the value of 4 right here. You take 1/2 to the fourth power, which is 1/16, multiply that to 48, and you get 3. So there's only 3 riders in the group of 50 to 59. Let's take a look at the table. So the table can also represent the coordinate pairs for when it comes to graphing, right? If you think about it, we have the verbal description, and from the verbal description, we made an equation, and the equation, we created a table, and we can actually use this table for that last step is to actually plot those points onto the graph. So in the table here, we have, again, we start out from 0 to 48, right? Because originally we started out with 48 riders in the 10 to 19 group. From 20 to 29, we had 24 riders, and that is being reflected there at the table. Again, if you're checking if it's a function, this is probably like the most well organized. It's like if any of those values are repeating itself. Now we can take our table and we plot it all into a graph. There is our exponential function, our decay function, right? And again, if I try to draw the vertical line test, oops, wrong color, red. So there we go. Hits one time. Now be careful, because when the line curves, and you draw that vertical line, for some reason, sometimes it looks like it's hitting more than once. But remember, it's a curve. So no matter what, it's only going to touch just once here. Let's go ahead and move on to slide 13 and take a look at each of these here to see whether we have a function or not. So let's take a look at the first one right here. Y is equal to 2x. So I can roughly graph it for you, but for every input, meaning that x part or x value, cannot repeat itself. So sometimes it is going to, if you have an equation, it's easier to go ahead and graph it out. I'm going to go ahead and do that on the right hand side. So y is equal to 2x. When I put 0, it's going to be 0, 1. And then 1, it should be 2. And then 2, that would be at 4. So it's actually an exponential function, an exponential growth, and it's curving off this way. So again, if I draw a vertical line test, this is the part where I say like kind of looks a little tricky, because remember, sometimes my lines, because it starts to continue getting really, really steep. And right there is probably the perfect time. What I'm just describing there is that, remember, it looks like it's touching multiple times, but because that line is still curving and it's getting so steep, when I draw a vertical line going down it, it looks like it's actually touching more than once. In this case, it's only touching once, just there. So this is considered a function. I think also if you click on it, it'll tell you if it's a function. So this is a function. So they test out those values for you and give a little explanation there. x is equal to y squared. You actually kind of saw a little bit something like that when I was bringing up the vertical line test. So x equals y squared is a line that look or a the equation is graphed like this. If I draw my vertical line test here, it fails. You can draw it here and say it only intercepts once, but if I draw another one over here, it fails as well. So once it fails, it it's considered not a function. And that idea about just to simplify when you have to determine if it is a function or not, say I take a look at like, okay, here's one and it's graphed at like, this is, let's say 2, and this is actually 1, it would be at 1, 1. So let me fix that. So I graph it here, this would be 1, and then right here would be at -1. So I have 1 comma 1 and 1 comma -1. Remember that input value has to be unique, meaning again, it can't repeat. So that's why this one is considered not a function. So again, let's go ahead and incorporate that little trick that I said to kind of summarize down for a function by looking at these coordinates here. So if I take a look, I have a set of ordered pairs. I'm going to just take a look at the x part and verify that it doesn't repeat. But it looks right here, -2 and -2. This is considered not a function because the -2's are repeating. If I do the same for over here, -1, -2, -3, -4, they don't repeat, so it is considered a function. When you have a table, again, you only look at where the x's or the input values. Here, it's the 4's are repeating, so it's not a function. Here, no repeats, so it is a function. And if we double check, function, not a function. Again, the vertical line test is applied at the bottom one here. For this parabola over here on the left-hand side, it passes because it only touches once. Again, there's no, for vertical line test, there's no specific way where you're going to go ahead and actually graph it. You draw as many as you want, but again, just to test it out and get a feel for it. Here, it passes not only once, but twice, so this is not a function as well. So again, the vertical line test is nicer, especially when you have a graph. Let's go ahead and take a look at key features. So we can learn a lot about a function by analyzing its equations, tables, or graphs. Let's look at the form of a linear relationship represented, the slope-intercept form. So by looking at the slope-intercept form, it determines key features. For any linear function, you are going to have a slope. And let's go ahead and just jump into that. So if we take a look at the values here, I'm actually trying to figure out, okay, so this table is the graph, it's graphed down below for us. So if you think about it, we start out with the equation at the top, f of x equals -3x plus 6. We have a table for it, and we have a graph. So this equation is represented to us in 3 different formats: equation, table, and graph. And that's how they're going to most likely give it out to you for the rest of this section in the tutorial. So here, by looking at the y values, we go from 9, 6, 3, 0. We're actually decreasing, so they got that arrow going down. But you can also read it in a graph once you're reading it from left to right. So like you follow along. So start from the left side of the graph or of the line, and you feel, and you're moving it towards the right, you're actually seeing that you're going in a downhill motion. So it's actually representing decrease. So another way to kind of state it too is that as x goes to infinity, meaning, so if we think about it in a number line, infinity is positive infinity is going off to the right hand side, and negative infinity goes off to the left. So it's kind of like 2 motions. You're moving it like in a horizontal motion, but you're also following it in a vertical motion as well, whether you go up or down. So as x goes to infinity, meaning once you go in this direction, what's happening to your graph? You're actually going down. So as x goes to infinity, f of x goes to negative infinity. So it says as the values of x approach. Now what happens if we talk about it in the reverse way? because that you're going to end up encountering both of them. So if I ask, let's go in the opposite direction. So as x goes to the left. So when we're reading this graph and we're going to the left, what's happening? My graph is actually going up. So then as x goes to negative infinity, meaning compared to the x-axis, I'm going towards the left, f of x goes to infinity. So let me write it out as well here. They wrote it out in as a sentence, but I like to just do the notation just super short. As x goes to positive infinity, and that again, that means off to the right, you can say f of x, or the y values, goes to negative infinity. So in this way, it's kind of like my short notation of what they're writing down here verbally. Then as you go to the right, we have as x goes to negative infinity. So as you move towards the left, your graph is actually going up this way. So then you say f of x, f of x goes to infinity. So that's one part of the key features. Key features, there's a list. Sometimes I can say, let me find do you have an x-intercept? Do you have a y-intercept? When is it increasing? When is it decreasing? It literally becomes a long list of things that are attributes that you look at the graph for. And sometimes like that saying, like a picture is worth 1,000 words. So you can technically, with a graph, you can see it a lot more clear. The next thing we're going to talk about are intercepts, is kind of what I said before. Does it have any x-intercepts? If it does, you're going to state it. Does it have any y-intercepts? So again, x-intercepts, it does intercept at 2, so your x-intercept is at 2, 0. It does have a y-intercept, you'll have it at 0, 6. Are you always going to have an x-intercept and y-intercept? No. But again, you're going to follow down this list of key features. And keep in mind, we're only talking about this one so far. How do I identify an x-intercept or y-intercept in a table? Because again, a graph, it's pretty straightforward. It's right there for you. It's nicely pictured. But if we're only given a table, you would look for the zeros. So if I look under the first column here, under x, I have a 0 here, so I'm going to highlight that. And I don't have any more zeros under x. Let's try f of x. So I have a 0. I have it right here. Can you also kind of tell right there? Those are the same numbers and coordinates listed in our graph for us there. So you might be given a graph, you might be given a table. You're going to have to consider both. Let's take a look at the next one. So the next one is finding the slope and determining it. So by the equation, if you are familiar with y equals mx plus b, it is set up in that form. So m gives you your slope. So the value in front of x is your slope. Right there, it happens to be -3. So the slope is -3. By looking at the table, you can take the difference. So like from 9 to 6, you subtract by 3. 6 to 3, you subtract by 3. 3 to 0, again, you subtract by 3, and you kind of get the idea there. Now, for the left-hand side, it is -1 to 0, that's add 1. 0 to 1, add 1. Plus 1, you get your 2. 2 plus 1, you get your 3. So then you take from the y side the -3 over that 1, and you still get the same results of -3. Another way to do it, again, it's the change of y over the change of x, or maybe you've heard it as rise over run. I would choose 2 points on the graph. So like I'll choose it here on my y-intercept and on my x-intercept. And I start with the far left point and I say, all right, my rise, if I go up, it's a positive. If I have to go down, it's a negative. So here I go down 6. So that's -6, and then I go off to the right 2 times. Now that doesn't give me -3 right off the bat, but if I simplify this, -6 divided by 2, we get our -3. And then let's go ahead and take a look at the next one, is when is a function positive and when is it negative? So again, like I said, the graph is a lot more nicer. The x-axis is kind of like that borderline. Anything above the x-axis is considered positive. Anything below is considered negative. How do we determine this in a table? You By looking at the table, you focus under the second column under f of x or the y. You focus on all your positive numbers, and then when you go from that switch to positive to negative, that is where that or any negative value is when it's considered negative. They are going to write this in interval notation. So if you think about this kind of towards, you reflect the graph in terms of like a regular number line. It's positive all the way up to 2. So let me kind of put this in red here. So everything right here, oops, in red, wrong color. All of this right here, meaning if this graph was to extend, it's all positive. So this is coming from the negative infinity side because we don't know where it stops. So it's positive from negative infinity all the way to 2. That's when it's positive. It's negative from that 2, and then it continues going on this way to positive, towards the positive direction here. So then it's negative when it's 2 to infinity. So we are going to be using a little bit more of interval notation to identify when we have it positive and when we have it negative. And we'll go ahead and practice more of that on slide 16. So let's go ahead and do an overview of this one. And this one is actually a quadratic formula. So this quadratic formula here, again, we're given it in 3 different formats. We have the top part, which is an equation, a table, and then the actual graph. So again, I like to base it off of the graph a lot, but there is going to be some key features that we're going to notice based off of this one. So the first thing they want to go ahead and do is determine the vertex. So before I click on this, how do we find the vertex here? By looking at the table, you're going to focus on that under g of x, or the output values. And you're going to find that middle number where it's kind of, that middle number is different. And then after the one above it and below it will actually repeat. So what do I mean by that? So if I look at it, I have 3 here and I have 0 below, nothing at the top. Let's try 0. 3 and negative 1. Always end up selecting the wrong color. 3 and negative 1 don't match. So 0 is not my middle number. Let's try negative 1. 0, 0, 3, 3. So this is actually my vertex, or that middle point right here. If you see it on the graph, that's your negative 3, 1. Now, if you strictly only have the equation for it, you can input it into a graphing calculator and determine it by that, or you can use the vertex formula there by determining first your a, b, and c, and then plugging it into the value of negative b over 2a. Once you plug it into that, you'll get the value of negative 3. That would be that x value. Once you get that negative 3, you plug it into the equation to get that negative 1 to give me the coordinate. So that's the vertex. That's how you determine it. It's like like an overview for both the equation, the table, and the graph. So the next one that they're going to determine is, or another way to how they determine a vertex is that for a quadratic, you're going to have a decreasing portion and then an increasing portion. Where does that switch happen? So if you think about it right here, it goes 3, 0, negative 1. So it's still decreasing, and then it goes back to 0, 3. So no, it was decreasing and then it's increasing. That's how the motion of those arrows are going down, decreasing, up for increasing. So they determine the vertex for you. And also, like I said, kind of like how I drew like those little rainbow loops that repeat. That's how you know you have that vertex there. Now, with finding the vertex, you also have the axis of symmetry. Axis of symmetry is, it goes through the vertex, and if you take a look at it, there's your dotted line right here. It cuts the parabola perfectly in half. Again, to find the axis of symmetry by looking at the equation, if you determine your a, b, and c, kind of like what we did for the quadratic formula in the last tutorial, you can plug it into x equals negative b over 2a. You plug it into that, those the b value and the a value, you actually get your axis of symmetry, which we can do that right now. B is the value of 6, so we have negative 6 over 2 times a is 1. So that is just negative 6 over 2. When you divide that, you get negative 3. So again, x is equal to negative 3. That's the same thing as your axis of symmetry. Oops, I clicked on the wrong tab arrow. Sorry about that. The next thing we are going to discuss is x-intercepts. So do we have any x-intercepts or any y-intercepts? So like I said, based off of the table, you just find where you have a zeros listed. So you have one like right here, one right here. They don't, now in the table it's limited, but in the graph you can see that you do have a y-intercept. It's just that the table wasn't like expanded more. But again, visually, you can see you have two x-intercepts, again, that you'll list, and then you have a y-intercept. How would you solve it if you, what happens if you didn't have the table or you didn't have the graph? You would use the equation and you would factor it. Factor and solve the equation where it's g of x would be 0, and you would actually follow the same concept rules that we learned in that previous tutorial. Moving on to the next part is when is it positive and when is it negative? So again, positive when it's above the x-axis, negative when it's below the x-axis. Or if you want to determine your g of x, so the blue is positive. Under g of x, you want to look at all the positive numbers. Zeros are included because it's kind of like that in between. And then you have your negative right here that's down below. So here, they're going to write the intervals for you. So if I think about it, this way. In terms of the, I'm going to use the x-axis to help me write out my intervals. From here to here is it's positive, and then from here to on it's positive. That little in between is when it's negative. I'll do that in red right there for you. So by using that number line, I'm going to generate an interval notation. So when is it positive? It's coming all from this side, which it forever comes from this way. So we'll just say negative infinity. So we start out with parentheses, negative infinity to negative 4. Again, I'm using only the x-axis to guide me for that interval notation. So it'll be negative infinity to negative 4, parentheses. Now, I have this decreasing, which I don't want to mention, but I do have another positive area, right? Not decreasing, sorry, negative. It's positive here from 2 forever going this way to infinity. So what I'm going to do is then there's a break. So I'm going to put U for union. We start out with negative 2 all the way to positive infinity. So that is when the function is positive. When is it negative? And that is from negative 4 to negative 2. So in interval notation, there is something very unique. You have parentheses and then you have brackets. Brackets means that it can actually be that value. Parentheses can be like it's getting closer to, but it's not. That's like the very similar ideas when we were writing our inequalities. How would we, if we would write a open circle or a closed circle? Parentheses are open circles, brackets are closed circles. Here we can't say it's actually negative 4 or negative 2 with the bracket because the negative 4 and negative 2 are like our in between. It's not positive, but it's not negative either. So that's when we would put as a open parentheses. So those are some of the key features for that lesson activity. So let's go ahead and take a look at this question right here on slide 17. Consider the exponential function h. So they gave us the equation and they gave us a graph, no table. Says function h is always decreasing or increasing. So again, if you follow your finger along starting from the left, what's happening is this function increasing or decreasing. Go ahead and answer that below. The function's blank is the function's x-intercept or y-intercept is located at 0, 5, and there's no blank. Well, 0, 5, if you were to plot that point on there, 0, 5, what is that considered? An x-intercept or y-intercept? Keep in mind, see what axis is it touching at? That's going to be your intercept. And then if you have that, it looks like it doesn't touch where? The function is blank for all x values. Is it positive or negative? So remember, the x-axis you're going to use as your borderline. This is a positive function. This is when it's up here is positive, and when it's down below, it is negative. So the function is positive or negative. Go ahead and determine that there. So go ahead and save this for part 2, slide 18.